Okay, hopefully that was enough time for you guys to fill out both these links. Make sure you get an account and tell us what your username is. I will put this page up again later when we go into our first example problem. So if you missed it, no worries. Okay. So if you want to see our example problems for this workshop, actually, unfortunately, the second example problem cannot be added to a contest, but you can use the link later. But if you want to see our first example problem and the rest of the problems which we will be putting in our contest for this week, which you'll have a chance to work on throughout the next 7 days, please go to this link right here, open.kattis.com/contest/QSSFSF, or you can go to the side link at the bottom of the screen and go to the side and just click on it. Either of them works, and please join the contest so that I know that everybody's account is working and they're able to join. And I'll give you guys 1 minute to do that. And can everybody just give me a thumbs up when they join the contest and they can see? Okay, cool. Awesome, awesome, awesome. Okay. So now let's talk about how we go about solving a problem. The general process is going to be to read a problem, code the solution using this little coding button. You can either upload a file or you can just start typing directly into the editor. What I always do is copy paste code from my own editor into the Kattis editor and then just submit that way. And then you submit your solution and you'll get something like what's on the right, which has a bunch of test cases and either little green check marks to show that you passed a test case for a given problem, or an X to show that you got some kind of wrong answer. And your goal is to submit the problem until you fix all of the bugs with it and pass every test case and get an accepted solution. So just to go over that one more time, basically, we read through and we understand every part of the problem. So make sure you understand the different bounds that the problem is giving you, what the input is, and exactly what you're supposed to do with that input and output. And then try to go about solving the problem, just, pen and paper on a notes app, however you want to, just figure out what the sort of trick to the problem is, what sort of algorithm it might be asking you to use, how you would really solve it. And then once you know how to solve it, implement that solution using code on your own editor, wherever you want. And then if you get one of those wrong answers, either time limit exceeded, just a regular wrong answer, try to figure out exactly why you got the answer and what you can do to fix it and debug. So hopefully you are all a little experienced with the code and you know all of that. And so now let's just get started with our discussion of graphs. So just give me a quick show of hands if you've heard of or used a graph before, not like X and Y, but like one of these kinds of graphs. A couple of people. Okay. Well, I will still go over everything. So if you already understood graphs, then you can look at some of the problems in the contest, or you can follow along here. But let's just talk about the basics of what a graph is in the discrete math kind of sense. So in graph theory, a graph is a set of vertices and edges. Vertices are also called nodes. If I say nodes sometimes, just know that they're the same thing. But it's essentially a concept which takes objects, which we represent as vertices, and then connections between those objects, which we represent as edges. When we talk about graphs, the main terminology that we use are adjacency, which is to say that two vertices are connected by an edge, and also the degree of each vertex, which is how many edges are connected to that vertex. So here you can see that the two vertices on the left are adjacent because they're connected by an edge, and these vertices on the right have the degrees as they're labeled, because the top ones all have one edge connecting to them and the bottom has 3 edges connecting to it. So we say the top ones have a degree of 1 and the bottom one has a degree of 3. And so when you receive a graph as your input for a problem, it's usually represented in this sort of sense of vertices and edges. Sometimes it'll be flavored so that you'll end up having to figure out how you're supposed to implement a graph and how you're supposed to create it. But a lot of times you'll just be given the information directly about what the vertices are and what the edges are. And in a math sort of sense, that's described as the set of vertices and the set of edges, where vertices are represented usually just by numbers and edges are represented as I, j, where in the edge is from I to j and vice versa. And in code, that will usually look like just a bunch of numbers. Usually you'll get this first line, which has the number of edges and vertices in a graph. And then you'll get a set of edges, for example. Like this is to say that there's an edge between 1 and 4 and between 6 and 8 and so on. And it won't always look like this. Sometimes you'll be given a matrix. Sometimes you'll be given some other sort of information, which you have to create your own graph with and figure out what the edges are. But oftentimes it will be in the simple sort of format of exactly what the edges are. And then you can assume that all the edges connect vertices that exist. So a couple examples, just to clarify, if you're wondering, well, what is the graph even used for? What's the point of this concept? Something you could do, for example, is represent social connections. So if you wanted to have a friendship graph, the vertices would represent people and edges would represent relationships between them, or maybe people who are friends with each other on a social media app. So if you want to find someone, if someone is in the same social circle, you can see if they're connected to each other on a graph of connections. And so this is a prime example of how we use graphs. And another one is to represent locations, physical spaces. In a neighborhood kind of graph, objects would represent, vertices would represent locations, landmarks, significant places, and edges could represent roads or ways to get between those places. And so you can see how this is useful in mapping things and understanding if you can get from one place to another, if you can't. And it has many applications depending on how you modify these graphs, which we will get into this workshop and the next. So just to go over a couple more graph terminology things, we might use the phrase a path, and a path is essentially what you would expect. It's just a grouping of edges from one vertex to another. So it goes from, for example, from A down to C, down to C2, down to C3, and so on and so forth. And this would be representative of the path that connects vertices A and B, and is represented by the edges A, C1, C1, C2, C2, C3, and so on until you get to the end. And a cycle is a special kind of path which ends at the same point that it starts at. So it's still a connection of edges that go from one point to another, but what's special about a cycle is that it goes back around to the start like a cycle. Now, we also often talk about directed graphs. So all the previous examples were undirected graphs, which means that if an edge connects I to J, then it also connects J to I. They go both ways. But a lot of times problems will have you need to express the idea that one thing leads to another, but the reverse isn't necessarily true. And for this, we use these directed edges or in a directed graph, which is to say that vertex A is connected to vertex B, but vertex B is not connected to vertex A. And we use this arrow notation just to show that clearly. And when we talk about directed graphs, we can no longer use the phrase degree because you have to identify whether the edges are going in or out. And so we have these two new terms, in degree and out degree, to talk about how many edges are pointing into a node or a vertex and how many edges are pointing out of it, which is kind of self-explanatory, but if you're confused, take a look at this. For example, vertex 4 has an in degree of 1 because 3 is pointing to it, and has an out degree of 2 because it's pointing to 1 and to 2. And a prime example of where you might see a directed graph is in a course prerequisite chart. Maybe you've seen this, or maybe you haven't, but this is the course prerequisite graph for CS majors at UCLA. And so understanding how this sort of graph works and how to navigate it can be important for a variety of reasons. But this is just one example of where you might encounter this sort of graph. So now let's talk about implementation. You know what a graph is, but how do we represent it using code? So as a quick aside, just to make sure that everybody knows what vectors are, we're going to just talk about them quickly, go through some of the syntax. If you haven't seen them before, they're like a lot like arrays, but vectors are a tool which doesn't need to have a defined size, and you can add elements to as you need them. And C++, in order to use vectors, you just need to make sure you include the library for them, which is #include vector. If you're on Windows and you're using bits/stdc++.h, then you're good, but just important to know. If you want to declare a vector, this is the syntax. You say what data type you want to put in it in those angle brackets. You declare a name for it. And as you can see, if you want to create a vector of ages of undefined length, you could just do vector angle brackets int and the name ages. If you want to automatically set the value inside of a vector, you can use this parenthesis notation where you say first the size, or n, and then the initial value of all the elements. So if you wanted to create a vector of ints, which are all initialized to 100, you could use this parentheses notation to make a vector size 5 with each value initialized to 100. And this works with strings, with whatever else you want to put inside of those angle brackets. To access elements in vectors is similar to array syntax. You can use those square brackets and just give the index that you want to access of a vector. You can also set elements in a vector using the same notation and equal sign. And so in a lot of ways, they're similar to arrays, but the main difference, if you want to read more about vectors, you can go to this link on the C++ reference page. But the main difference is this bolded line here, vec.pushback. When you want to add elements to a vector, you can just push them back to the end. You don't need to set exactly where it is because vectors are dynamically sized, which means that they will grow and shrink according to how many elements are in them. And so you can just use pushback in order to directly insert a value to the end of the vector, which is a really useful tool in competitive programming because you will a lot of times have to add elements without knowing how many are going to be there in total. The 3 bolded or 4 bolded things are the 4 main things you need to know about vectors. If you didn't pay attention to any of that, that's all you need to really know is that you need to include the vector library. That's how you declare a vector. You can use the size of it in order to iterate through it or something, and you can push back values to the end. Okay. Does anyone have any questions about vectors or any not understanding? Okay, awesome. So now let's talk about how we implement graphs. The 2 main ways are with adjacency lists and adjacency matrices. So let's talk about each of these a little bit more in depth. With an adjacency list, the idea is that we have a vector of vectors or an array of vectors where each entry in our array/vector, our outermost layer, refers to a certain vertex in the graph. So this is representative of a graph with 3 vertices, for example, 0, 1, and 2. And for each one, we put a vector in that slot in the array to represent all of the nodes that are adjacent to that vertex. If you have an array of size n, that does the same thing as using a vector for the outermost one. But using a vector inside those array indexes is important because it lets you just push back elements as you discover that they're adjacent, either as input or through your problem creation. So as an example, if we have this graph on the left, then we can put it into this adjacency list on the right. We have 4 rows to represent the 4 vertices in the graph, and they're labeled with the indexes of the same vertices they represent. And the elements inside of each vector at each array index are representative of what vertices are adjacent to that given vertex. So just to go through a quick analogy, if you go to 1, you can see in our adjacency list that in the vector for 1 is 0, 2, and 3. So it should be adjacent to vertices 0, 2, and 3. And you can see that there's an edge between 1 and 3, 1 and 2, and 1 and 0, which correctly identifies that relationship. And the same holds true for 0, 2, and 3. Any questions about adjacency lists for now? So let's try an example. Can anybody tell me how you would represent this graph in an adjacency list? Just tell me what each of these different indexes should have in their vector. Yes.
So for 0, it would just be 3.
Yeah.
For 1, would it be 2 and 3?
Yeah.
And for 2, would it be 1 and 3?
Yeah.
And for 3, it would be 0, 1, and 2.
Lovely. You got it exactly right. And you win a raffle. You fill out your name and give it back to us at the end of the workshop. It will be a raffle ticket digitally for next workshop. Yeah. Now, if we want to represent directed graphs in an adjacency list, it looks a little bit different. As you might have guessed, instead of having every single one in, like if 0 is connected to 1, 1 is connected to 0, we just do this notation where if it's pointing to another vertex, then we add it to that vertices list. Otherwise, we do not. So, for example, 0 is pointing to no other vertices, and so it has nothing in its vector list, whereas 1 is pointing to all 0, 2, and 3, and so it has those numbers in its list. Okay, can somebody else tell me how they would represent this adjacency, this graph as an adjacency list? Anybody? Yes.
So 0 will have one.
Yeah.
One will only have three. Two will only have one. And three will have one and two.
Awesome. Perfect. And you win. Yeah.
Thank you.
Thank you very much. And so just to go over how that looks exactly like in code, this is for C++ specifically. If you want to figure out how it works in Python, there's a million websites and links out there to look at, but this is how the syntax sort of looks for setting up an adjacency list in code. We declare it as a vector of ints that is an array. So that is to say that we create one array index for each vertex in our graph, and then we put a vector each one. And then in order to add elements to each of these, you can index into the vertex that you want to add adjacent vertices to, and then push back the values that you want to set as adjacent. So if you want to say that 1 is adjacent to 0, you access the 0th element of our array in order to push in the number 1 to that vector. If you want to check for adjacency, all you have to do is iterate through one of those vectors. So if you want to see if 0 is adjacent to 2, then you iterate through all of the adjacent vertices in 0's vector, and you can check if the value is equal to 2, which is to say that 0 would be adjacent to 2. And so just to show what those pushback commands are doing, 0 is adjacent to 1, 1 is adjacent to 0, and 0 is adjacent to 2. Okay. So now let's talk about the other form of representation, which is adjacency matrices. So the idea here is that we create a matrix, a vector of vectors if you want, but usually just an array of arrays, as long as you know how many vertices are in your graph, where an entry in this matrix is a 1 if there's an edge between that row and that column index, and a 0 otherwise. So as an example, we could put a graph into adjacency matrix this way. So you'll see that the matrix is symmetric because in an undirected graph, if 1 is adjacent to 0, 0 is adjacent to 1. So if you go over to the matrix, you should see that 0 is adjacent to 1 and 1 is adjacent to 0. So for undirected graphs, adjacency matrices will always be symmetric, but you can kind of just directly check if something is adjacent and set those values as needed, because all you need is the index of the row and the column, and that gives you your vertices that you're working with. So can anybody tell me how they would put this graph into adjacency matrix? Sorry. Anyone can answer. Just tell me how you would like fill out the 16 boxes from reading order. Anybody? Yes, Robert?
I get started. So there are no edges from 0 to 0, or 1 to 1, and 2 to 2, and 3 to 3. So it's all zeros along that diagonal.
Very good. Yes.
Look for this.
0, 0, 0, 1, 0, 0, 1, 1, 0. Let's check. How about that? Yes, you got it. Very nice. So just to make sure that everybody understands what's happening, as Robert said, all of the diagonal is zeros because there are no self loops here. So any node or any vertex is not adjacent to itself. So we put a 0 in the, I column row sort of deal. And then if you look at, for example, the third row, you can see that 2, which is the row that we're working with, is connected to 1 and 3. So if you go to the 1 and 3rd column, knowing that this is 0 index, so it starts with 0, then we put a 1 there. And if you go to the 0th and 2nd column, you can see that there are zeros there because 2 is not connected to either itself or to 0. Okay, let's go through one more example with a directed graph. So in the same way with the adjacency list, where the convention is that the row kind of points to which ones are adjacent to it. This case, we use the row points to the column. So that is to say that if we look at, for example, our first row here, not the 0th row, but the first row, then you can see that 1 is pointing to 0, 2, and 3. And so at the 0th column, the second column, and the third column, we put a 1, and then it's not pointing to itself. So in the first column, there's a 0. So if you want to say that 0 is pointing to 3, then you'd go to the 0th row and the third column and put a 1. And otherwise, it's a 0 to represent the lack of that connection. So, oh yeah, here's a good circle. From 2 to 0, you go to the second, really third row, and the 0th column, and that's why there's a 1 there. So can anybody tell me how they would put this graph into an adjacency matrix? Yeah, definitely.
Okay, with 0, 0, is that 0,
Yes.
0 to 1, with that 1?
Yeah.
0 to 2, 0,
Mm-hmm.
0 to 3, 0.
Yeah.
1 to 0 is 0.
Yeah.
1 to 1, yeah. 1 to 1,
1 to 1.
yes. 1.
No, 0.
0.
Because 1 is not pointing to itself.
Okay. Okay. 1 to 2, 0.
Yep.
1 to 3, 1.
Yep.
And 2 to 0 is 0. 2 to 1 is 1.
Yeah.
2 to 2 is 0.
Yeah.
2 to 3 is 0.
Mm-hmm.
3 to 0 is 1.
Yeah.
3 to 1 is 1.
Yeah.
3 to 2 is 0. And 3 to 3 is 0.
Awesome job. Nice.
Yay. Thank you.
Okay, cool. So does anybody have any questions about adjacency matrices and how they work for either undirected or directed? Also, just as a note, if there is a self loop, then you can put a 1 in the diagonal. Self loops are sometimes represented in graphs. I don't think we'll have any today, but it is a concept to be aware of. And so if you want to represent this in code using C++, how you do that is defining your adjacency matrix. A lot of times it's easiest to use a Boolean because we'll only ever use 0s and 1s here, unless we use weighted graphs, but we're not going to talk about those today, maybe next workshop. And if you want to initialize even a 2D array to a value, you can just set it equal to this curly braces with what you want to set it to. And so you can use 0 or false here to represent that everything starts off as a non-existent connection. And then if you want to add edges or to say that there is an edge between a given row and column, then you just set that row and column index to 1. So super easy. If you want to set 0 and 1 to be adjacent vertices, then you just set adjacency matrix, brackets 0, brackets 1 equal to 1. And you can do the same for any of them. And you can remove connections this way. However you want to modify the matrix, this is how you do it. And to check adjacency is super straightforward. All you have to do is go to that row column and see what the value is. And so because we're using a Boolean matrix in this example, if you just directly check the value, if it's a 1 to say there is a connection, then you can do something. And if it's a 0 to say there's not a connection, then the if statement will continue on. Any questions about how we represent this using code? So just to go over a couple of the differences, maybe you're wondering, well, why are these two implementations around and when do I use one? Why do they both exist? Well, this is the answer. Essentially, a adjacency list is best for a graph with few edges, and adjacency matrix is best for a graph with many edges. The reasoning behind this is that adjacency lists are space efficient. They only store the edges that exist in the graph. So you only push back into your vectors edges that are given to you or that you find exist. But it's kind of slow to check for adjacency, because if you get these really massive graphs and you end up having one vertex connected to a ton of other ones, in order to check all of its adjacencies, you need to iterate through the vector and check each one. Whereas with adjacency matrix, you might end up wasting a lot of space if you have a graph with a ton of vertices, but like only a few edges to represent sparse connections. Then you're going to have a lot of zeros in your matrix, which are just taking up space. But the pro is that you get to check adjacency really easily. If you want to look and see if two vertices are adjacent, it just takes one array access. So that's kind of the trade-off. And just to give you a visualization of what that looks like, if we represented this graph on the left here as adjacency list and adjacency matrix, even though it's small and usually you'd probably have something far larger for your test cases in a competitive programming problem, you can see the difference already, which is that adjacency lists will only store 8 integers because there are only 8 edges. Well, 4, but they go both ways. And it could take you up to 3 checks to determine adjacency though. For example, you can see that 3 being adjacent to 2 is in the 3rd index of our vector for that array index. And so if this starts to get really out of hand, it can get long, and suddenly checking adjacency, which may have to happen all the time, can start to add up and not be a constant time operation. And with a matrix, you can see that we store more integers. We need, n squared, where n is the number of vertices, but it only ever requires 1 check to determine adjacency, which is going to be either as fast or faster than using adjacency list. Does anyone have any questions about when to use a matrix versus when to use a list? Okay, so now let's go to our first example problem for the day, which is going to be weak vertices. Here's the contest link. Hopefully you all have already joined. If you haven't, please fill out both these links. I think everybody should be good now. But just open up problem A, weak vertices, and start reading the problem statement, which I'll throw up here. Well, if anyone needs the link. I will give you guys like 2 minutes just to read through the problem, and then I will go over what it's saying in case you're confused. So no worries. Okay, hopefully that was enough time for you just to get an idea of what the problem is asking. You don't have to understand everything it's saying right now, because we will go over it. But essentially, what this problem is asking is for you to find what vertices in a graph are weak. And what they mean by weak is that it's not part of an immediate triangle. So for example, in this graph, a very simple, small example graph, the bottom vertex is the only one that is a weak vertex because it's not part of a direct triangle. Even though it's part of this larger triangle, there's a vertex in the middle, which is creating a break in the connection between its 2 adjacent vertices. And so it's not part of an immediate triangle, and as such is defined as a weak vertex for this problem. So our job is to find the weak vertices just given a graph. And the simplest way to do this, which is probably not the best way, but is effective for this problem and is perfectly viable, is just to check if it has 2 adjacent vertices, just check if there's a connection between them. If there is, then it's part of a triangle, and so it's not a weak vertex, and we can move on. But if you check every single list of adjacent vertices and the connections between those vertices, and you find that there are no connections there, then you can finally determine that that vertex must be weak, as it's not a part of any immediate triangle. This last line kind of talks about the bounds for this problem. We're not going to get too much into time complexity today, but if you know what that is, then this brute force method is effective for this problem because there are only up to 20 vertices in our graph. And so even with the n cubed method, it will still run in time. If you don't understand that, that's fine too. Don't worry. So let's get into coding a solution to the problem. So here's a little bit of a code template. I will also hand out some worksheets If you don't have any pencils, let me know. I have a couple and some Sharpies. You're free to work on it with the people around you. I encourage, if you can, to talk it out with people, work on it together, see if you can come up with a solution in pairs or in groups, as you want. I'll leave each of you on work just so you have some space to work through on. And after done passing them out, read a pencil. I'll give you guys a few minutes just to get through as much as this as you can. You don't have to be super precise, just try to give the idea of what you would do. And then I will give you a little bit more information and some more code, and then there'll be like one big blank to fill out at the end. If you can do it all right now, go for it. But yeah. Okay, sorry that was not a lot of time, but you'll have a few more minutes to work on the last part. But I'm just going to go over a lot of the reading in the stuff and printing it out so that you can focus on this main block in the middle. Just to give you a little bit of explanation off the bat, this outer while loop is for a weird thing this problem does. Not all problems will do this, some of them will, but they give you multiple test cases for each test case. That is to say that when we read in this int n, we're getting the number of vertices for that specific problem, and then we have a while loop to keep checking the value of n and going and getting a new one, because if you notice in the problem statement, it says that the end of the input is marked with a -1 for n. And so you'll keep getting test cases until you get a -1. So this setup is just to say that we keep processing each test case in order. And if you are struggling with a couple of those to-dos on the worksheet, here's answers for 4 of them. This is just one way to do it. Of course, you don't have to do exactly like this, but we're using an adjacency matrix in this case, just by creating this 2D array of size n and n. And then we create a list, a matrix, an array of the weak vertices of size n. So we keep track of which ones are weak and which ones are not. And then the first thing, what I mean by initialize that matrix or that array is just to set every value equal to true. So we just assume that every matrix is weak until we prove that it's not by finding a triangle, which is what you have to do in the last section. Then to read in the graph, it's just a double nested for loop where you see in the values that you're given as input directly into the array indexes of your matrix. So it's super simple just to read in all of the different values that they give you, because you can just put them in at exactly the spot they're supposed to be, because they give you n by n values. Then at the end, you will just see out each element in your weak array as long as it is weak. And then you see out end L to do a new line, and you continue the loop. Is there any questions about any of this part of the code? Yes.
Would it be any harder to assume that they're all not weak and prove that they are weak?
Probably not. It might be a little bit different, but that is fine. You just have to check every single connection and make sure that all of them are non-triangles. Whereas this way, you only have to find a triangle, and then you know that it isn't weak. So it's probably a little bit easier, but it's the same overall. So. Okay, I'm sorry that was very little time, but we only have half an hour-ish left. If you guys are down to stay a little bit late, we will have a Kahoot at the end, which might run over. But I'm just going to give you guys the final little bit. Sorry, I didn't give you enough time to fully solve the problem if you're still working on it. But essentially, it's just this triple nested for loop with an if statement. So in order to check if there is a triangle, you can just go through every single possible triangle that could exist. So for every single I, J, and K, you iterate over all the vertices and you just check if there is a triangle, aka a edge between the first two, the second and the third and the first. And so using I, J, and K in a triple nested for loop, this is the brute force solution. There are probably better ways to do this. They're more efficient, but this passes the test cases for the problem, and so it works. And you just check. And if you find a triangle, then that vertex must not be weak, and so you can set weak I equal to false. This does work the same way, the other way. But yeah, there's just one possible implementation. There are better ones, but this is a solution that will pass. And so if you want to copy this code from the slides or write it down and submit it on Kattis, you can get an accepted answer, and that will be a raffle ticket for next week if you come. Any questions about our implementation for this problem?
Yeah.
Okay. So now let's get into some graph traversal algorithms. This might have to be a little bit quick, but essentially, now that we know what a graph is, how to implement it, how to do problems with it, let's talk about how we go through a graph, how we actually visit all of the vertices in it and do something with them. So there are two main ways that we do this, and these are the two most kind of popular graph traversal algorithms, which are breadth first search, or BFS, and depth first search, or DFS. So first, talk about BFS, or breadth first search. Essentially, what this means is when you're given a graph, like this one on the bottom, and you want to explore all of its vertices, BFS explores them outwards, like a ripple in a pond. And so to give you an example, if you were to use BFS, you would first visit nodes 2 and 3 right next to it, and then you go out one more layer over to nodes 4, 5, and 6. And so this is the order of traversal that BFS uses. And if you're confused by that, here's an example using a maze. I really love this GIF. But if you wanted to represent a maze as a graph, like how you would do so here, where each square in the maze is a vertex, and then edges represent valid paths through the maze, then BFS would explore the maze like this. And you can see the exits in the top right. As soon as it hits the exit, it resets. But essentially, this is used to find the shortest way out of a maze, because you're expanding your length every time that you go through a new layer of this BFS traversal of a graph. So let's talk a little bit about a data structure called a queue. Maybe you've heard them before, maybe you haven't. Essentially, a queue is a data structure that you can interact with in two main ways, which are to push things to it, which is to place them at the back, like the same way that a regular queue or a line works at a store. And then you can pop things, which is to remove them from the front. So what's important to note is that this is a first in, first out algorithm, which is to say that, or data structure, which is to say that things that are put into the queue first will come out before other things that are added to the queue. So it's just like a line in a store, if you think of it that way. Yeah. So just to give you a quick example of what I mean by that, if you add 3 numbers into a queue like this, then you go through them in order from top to bottom. If you want to use queue syntax in C++, here is a little cheat sheet. These are the most important operations you need to know. They're kind of like vectors, but a little bit different. You can push things, which places them into the back of the queue. You can access the front element and then pop it off. And then you can check if it's empty. And you just declare it kind of the same way as a vector by using queue angle brackets, the data type that you want, and the name. And you have to include the queue library if you want to use them. But it's a great tool for implementing BFS. So let's talk about what BFS looks like by hand. So if you're confused by the concept and what is going on in BFS, let's talk about it like more in depth. So given this graph, to implement BFS by hand, basically all we want to do is record the unvisited adjacent vertices of the node that we're on. Then we want to mark that node and the ones adjacent to it, once they're added into our queue, as visited, because they're on the queue already, so they're visited theoretically. And then you want to explore the next vertex, which is pointed to by our next arrow. So what that looks like is from our starting vertex, we mark it as visited because we started there. And now we add its adjacent vertices, which is in this case, is just 5. We put it on the queue and we mark it as visited because it's on the queue. And then we go to the next thing in the queue, which, as you probably guessed, is 5. So now we are at the 5th vertex and we check all of its adjacent vertices. So we remove it from the queue, we add all of its adjacent vertices, which in this case are 2, 9, and 10. And once they're on the queue, we mark them as visited so we don't go back to them and do over our work again. And now we go to the next element in the queue, which is pointed to by our little next arrow at the top of the queue, which is going to be 2. And so we go to 2 and we add its adjacent vertices into our queue, which are 3 and 6. And now we go to where our next arrow is pointing, which is 9, and we continue on. 9 has no adjacent vertices. We just cross it off and keep going. Or no unvisited adjacent vertices, excuse me. And then we go to 10, we see it has 1 unvisited adjacent vertice. 5 is already visited, and so we need to add 14 to the queue. like that. And we go to where the next arrow is pointing 3, and so on and so forth. And hopefully this continues until you reach a goal, like at the end. But in order to implement BFS, there are basically 2 things that we want to keep track of, which is what vertices we've already visited, which we can just use a Boolean array for. And then we need to keep track of what we want to visit next. And that's what our queue is used for. So now you know how a queue works, and you know how arrays work. And so that's all we need in order to implement BFS. If you can go to the next slide, you'll see the BFS pseudocode. So essentially, all we have to do in order to implement this algorithm is to create our queue. We mark our starting vertex as visited and put it into the queue in order to get started. And then, while the queue is not empty, we remove the vertex at the front, aka access it and pop it. And then we put all of its unvisited neighbors into the queue to make sure that we visit them at some point. And we mark them as visited to make sure that we don't visit them more than once. You can go to the next slide. You'll see the example code. So in C++, using a adjacency list, FYI, this is sort of what it looks like. You don't need to understand every little bit of this, but basically what is going on is we create the queue, we push in the starting vertex, which is passed into the function in this case, and then we set that value equal to true. And then while the queue is not empty, we get the next element by accessing the front of the queue. We pop off the front element, make sure that it's gone and we don't go back. And then this part here, it has some weird syntax in order to show that we're iterating through every adjacent vertex in our list, but we use the vector syntax of .size in order to find how many elements are in it, and then we use I in order to index into them here, here, and here. And so a better way to do this, if you haven't seen it before, is in C++ and a lot of other languages, there's this colon notation, which is used to just iterate through automatically all of the elements in a vector. And so if you just say int neighbor colon adjacency list next, that basically is saying in the adjacency list for the next vertex, which we're going to check, that is to say for all of next neighbors, we can do something with each of those neighbors. And so we can just check directly if it's not visited, then we put it into the queue and we mark it as visited. And we do that for all of its neighbors. And once we're done with that process, we go back to the top of our while loop and we access the next element in the queue. So as long as there are unvisited elements in the graph, we'll keep finding them and adding them to the queue until we reach the end, at which point the queue will be empty and then BFS will return. This is missing a key step sort of doing something with this information. Normally BFS has some sort of goal, but this is just the overall idea of how you would go through each vertex. And maybe once you find a given vertex that you're looking for, you can just stop, something like that. So let's go over quickly the shortest path algorithm. We have this cute example of 6 degrees of Agar. Maybe you've heard the 6 handshakes rule, which is also known as the 6 degrees of separation theory, which claims that we can get to know anybody just through 6 different connections. And so hearing this, you, a massive Agar fan, you want to know how many people it would take you to connect you to Agar. And so we're basically checking, is the 6 handshakes rule true? So let's imagine that you've got a list of everybody that you know, everybody Agar knows, and everybody that they know, and so on and so forth. So you can start creating this graph. And so let's say you found out that Agar is friends with Akash, Ilya, and Charlotte, and then you find out who Akash is friends with, who all those people are friends with, etc. And then you are friends with Tony and Lenny. And so you want to find how many connections it would take to get between these different people. So like I said earlier, you can use a graph to represent social connections. So in order to represent friendships between different people, which are represented as vertices, you just add an edge between them. And so you can add an edge between Agar and all the people that he's friends with. You can add an edge between Akash and all the people that he's friends with, and so on and so forth, until you get this sort of graph representation of you versus Agar and all the social connections between you. Now, if you wanted to find the shortest path between any of these two people, it's kind of intuitive. You simply go from one point, either your endpoint or your start point, and you work your way outwards, which is just a direct implementation of BFS. So the shortest path to any person right next to Agar is clearly 1. And then if you go outwards from each of those, the shortest path will be 2. And from those, it'll be 3. And you can just keep doing this until you get to yourself and any other node in the graph. And you can see that by definition, the shortest path from you to Agar for this graph would be 7. So in this case, the 6 handshakes rule is not true, but this is a useful tool for defining how many connections it takes to get from one point to another point in a graph. So as you just saw in our example, we were able to find the shortest path between you and Professor Ager pretty easily. So when we were considering a vertex V, we used the fact that we already knew the shortest path to an adjacent vertex U, and then we just added 1 to it. In a weighted graph where all the edges aren't 1, this could be different, but we're not going to talk about those. So for this case, basically you just add 1, and as you expand outward, and that creates your shortest path length to each vertex in the graph. And using an array, you can basically just keep track of these distances. And you just say that the distance to a given vertex U is just equal to the shortest distance to an adjacent vertex V plus 1. You have to make sure that you check all of the adjacent vertexes and get the lowest value in order to minimize your shortest path. But this is overall the notation. So just a quick recap of what I'm saying. In order to find the shortest path from one vertex to all the others, you just use BFS. You basically implement it, and all you need to do is keep track of one more array, which is your distance array. And you can just update it as you find these new connections through BFS by adding 1 to the adjacent vertex's shortest path distance, which is tracked in your array. Does anyone have any questions about how we find the shortest path on a graph using BFS? Cool. Okay, now last part of our workshop will be taught by Jay. He's going to go over DFS and another example problem.
First of all, how many people need to go at exactly 7:30? Because I can go really fast if you have to. All right, so yeah, let's just go really fast. So we have a little over 10 minutes to go over this. All right, so DFS is pretty much the same thing as BFS, except we traverse our graph in a different order. So before in BFS, it was kind of like in a pond where it ripples outwards, but here in this case, we're going to explore all the way down the entire path until we backtrack and then explore a different path. So here in this example, we can show this in a maze. So no, we're not going to finish otherwise. We'll finish. Okay. So in this maze, you see that before where it like slowly spreads out from the center, here it tries to explore all the way to the end until it tries a different path. So here it goes all the way to like the corner, and then it goes to the other side. And the way that you can implement this is the same way that in a queue, you add everything into it for BFS. For DFS, you use a stack instead. So the difference in a stack and a queue is that in a queue, the things that you put in first will be taken out first as well. But in a stack, the things that are put in last will be taken off first. So this causes the difference in our traversal order, where in the queue, it accesses the things that are closer to the center first. But here, the things that are farther will keep getting taken off of the stack. So you'll get this effect where you explore all the way to the end before going back. So here, we can demonstrate this with the same graph. So here we add 5. Also, I flipped the order here so it represents the stack more clearly. So we put 5 onto our stack, and then we take 5 off, add all of its adjacent neighbors. So here we add 2, 9, and 10. And then we take the top element, which is 10. We take that off the stack, and then we add the adjacent neighbor of 14. From here, we take 14 off, and we add 13 and 15. And then we take 15 off, and we add 11. And here you notice that we've kind of gotten pretty far from our starting point without exploring all of the nearby neighbors. So using a stack rather than a queue, we get this effect where we explore the whole path before we switch to a different path. And this is the syntax for a stack. It's pretty much the same as a queue, but rather than accessing the front, we access the top. And this is the exact same code, except you replace every instance of every instance of queue with stack. And instead of front, you use top. So yeah, this should look very familiar. We just went over this a couple minutes ago with breadth first search. But you might be wondering, like, why would you need to know both? The main reason is because you don't actually have to implement depth first search this way. There's a better way to implement depth first search, and it's by using recursion. So if you're not familiar with what recursion is basically a technique where a function can call itself in some way to solve sort of like a sub-problem. So when we're calculating, for example, factorial, one way to calculate n factorial is to just multiply from 1 all the way up to n. But instead, you could calculate n minus 1 factorial. And then after you calculate n minus 1 factorial, you just multiply n on top of that, and you get n factorial. So how this applies to depth first search is in depth first search, we can also utilize a similar idea of recursion, where in this case, we start at 1, and then what we want to do is we want to traverse the whole graph, right? So we can pick at 2, we can say like, now imagine 2 is our route, and we traverse everything after 2. And then after we're done with that, we go back to 1, and then we say we traverse everything at 4. And then we traverse everything from there. And once we're done with that, we know that we've traversed the entire graph. So putting this example into code, the way that it would look is like this, where like our depth first search function would want to traverse the entire graph. So here, like we mark the vertex that we're currently at as visited so that we don't go back to it later. And then for each adjacent vertex, we say we run DFS recursively on that vertex, so it will traverse everything on that side. Yeah.
Can you explain the syntax on the fourth instance column?
Yeah, what this syntax means is that it just traverses everything that's in that vector. So in this vector, it'll have, for example, like 3 things that are adjacent to it. This is just a shortcut way to say like, okay, we take each element in that vector rather than like using the index notation that you're familiar with for an array. But if you're not familiar with this notation, you can of course always just use your standard index, like for int I equals 0, I is less than list.size, I plus plus, so on and so forth. So yeah, and like going back to how we implement DFS recursively, it's just you go to all of the neighbors and you recursively run depth first search on it. So like depth first search it would just traverse everything on that path basically. All right, so I know I went really fast here. So now is a good time for any questions about things that you would want me to go back and cover a little bit slower. Yeah. Yeah, so this is kind of a case where, and also that little comment there is just, if I don't know if any of you use Python, but anytime you use recursion in Python, you'll probably need to increase the recursion limit, but that's
What's the recursion?
in Python it's 1000. So if you want to go more than 1000 times recursively, you would need to increase it. Also the difference between depth first search and breadth first search, in like things like software engineering, there's legitimate use cases for both, because sometimes like one way of traversing would get you faster results on average. But in competitive programming context, you generally want to traverse the entire graph. So the order doesn't really matter. But again, like in breadth first search, you can use it for the shortest path algorithm because like it slowly expands outwards, so you can keep track of your distance. For depth first search, the main use case is just in competitive programming, this is a lot faster to type, and speed matters in competitive programming. So most competitive programmers would prefer coding this just because it's easier to implement. So that's why it's good to know. All right, so here's like a little comic again. Depth first search, you go all the way to the end of the path before going back and trying a different path. Breadth first search, it kind of just slowly branches out, and you can ignore the rest. All right, so if you go to this link right here, we have a more difficult challenge, and here we'll need to use one of our graph traversal algorithms. This one is unfortunately not on the previous contest link, so you'll have to manually type in this link. And yeah, also you can, for the sake of time, you can ignore most of the text at the top. It's pretty much just flavor text telling you that there is a secret chamber behind Mount Rushmore. You don't really need to know that. The main important part is near the bottom. So yeah, I hope most people have at least had a chance to read most of the problem. I'll quickly summarize what the problem is asking. So basically, you're given a list of possible translations where a letter can be converted to a different letter. And then you're given 2 strings, and you try to convert each corresponding letter of the 2 strings to each other. So first of all, this might not immediately seem like a graph problem. So we'll just quickly demonstrate why this is in fact a graph problem. So you can think of converting a letter as going from C to T, for example. So like here, the input means that C can be converted into T. You can represent this in graph form as C can go to T. And then similarly, I can go to R, K can go to P, and so on and so forth. So here, by drawing which letters can go to which letters, we can kind of see that this is a way of representing it as a graph. And then now, like, we should also ask, so how does this graph help? So for example, let's say I want to say which letters that O is connected to. Can anyone tell me which letters O can be converted into? Yeah, so O can be converted into C. And then the problem also says that your letters can be continuously converted. So O can also be converted to what C could be converted into. So O can be converted into everything that's after this part. So this kind of reminds us of our graph traversal algorithms. So you are using our graph traversal algorithms, you can figure out if we start here, everywhere that we go to, we can try to get to everything. And if one of them is the letter that we want to convert to, so for example, when we want to convert can into that, we see if C can be converted into T, and we can run our graph traversal algorithm starting from C and see if we can reach everything else. So this is kind of the main idea behind this problem. And we have some template code to get you started as well. This is actually on the back of the previous worksheet you had. This might look a little bit daunting at first glance, but this top here is just a way to represent your graph. So since there's only 26 letters, we only need our graph to be 26 big, basically. And so you can either choose to use an adjacency matrix or an adjacency list, use whichever one you're more comfortable with. And for our graph traversal algorithms, we also need a visited array, which we've already declared at the top. And so for this problem, you'll need to implement a graph traversal algorithm. We recommend doing BFS. And you'll also need to implement the main body of the code, which is how you can use your DFS traversal algorithm in order to actually solve the problem. So this, we already have the input set up for you, but you have to take in the input and represent this in your graph. So for example, this means CY can be converted into C2, but you'll have to figure out how that can be represented in your graph. And also, when you compare two strings, you'll have to implement how that, whether or not it can be converted or not. Also, if anyone has questions, now is also a good time to ask. I can answer any questions about either DFS, which you went over really quickly, or anything specific about this problem. If you want, we can also probably just have people help you guys individually. You can probably just raise your hand, and we have a lot of officers here that can help.
Unrelated to the code, how do we find out when one learns where the next
We'll be here every week except for week 5. So next week we'll still be here, and then we'll send out something in the newsletter and on Discord and on
Awesome.
Instagram.
Yeah.
Thank you very much.
Yeah, if anyone needs to go, it's now 7:30, so you can go. And if you want to try this problem out on your own, you can also just message us on Discord if you need any help, and we'll be happy to help.
Thank you.
And yeah, if anyone does have extra time, you can feel free to stick around and we can answer any questions or help you guys out on the problems.
And we have a Kahoot also, if you're able to stay.